Okay. Sure. Okay. So this is a proportion because I just have two fractions that are equal to each other. So I'm just going to use cross multiplication here. And just, oops, maybe we'll do that. So that gives me 4 times x minus 4 times x plus 4 equals 4 times x squared plus 2x minus 8. I'm now going to multiply everything out. I'm going to do that all in one step, if that's okay with you, Maddie.
Mm-hmm. For the x minus 1, x plus 4, you'd factor that. Just factor it out.
You mean FOIL?
Mm-hmm. Fine. Sorry.
That's okay. Yes. Okay. So now what I'll do here is I'm going to subtract 4x squared from both sides, which just cancels those out.
Mm-hmm.
And then I'm going to add 32 to both sides. And then if I divide both sides by 8, I get x is equal to -4. However, if I try to plug that back in, I can see pretty quickly here that it's going to give me a 0 denominator.
Mm-hmm.
So I should discard that. And since I have no other solutions left, I'm just left with saying that there's no solution here.
Okay.
Mackenzie? Yes. Any other follow-ups on 3 before we move on? Maddie, are you happy?
Yes.
Okay. Very good. So 6 is decidedly not a proportion, right? Because on the right-hand side, I have two things being added together. So I'm going to start by factoring any denominators that are possible. I see that I do have one denominator that I can factor. And now I'm going to look at the least common denominator for all of my fractions. So it should be hopefully easy to see that that least common denominator should just be x plus 3 and x minus 2. So I'm going to multiply both sides then by that least common denominator. And then I'm going to write out what I get here. Again, as you're getting more comfortable with this process, if you end up starting to want to, if you show me what you multiplied both sides and then you don't write out this step where we're doing canceling, if you just go to the next step, that's going to be okay also. But if you're like, I can't keep it all straight in my head, no worries, you just write it all out. It's not a big deal. Eventually, at some point, I'm probably going to quit wanting to do that, but we didn't do a lot of examples of this process when we did the lesson, so I don't have a problem like showing a lot of detail here. So far, so good, Maddie? Okay. So let's go ahead and start canceling things. So I'm left with then just 5 equals 2 times x plus 3 times x minus 2 plus x plus 3 times x plus 3. Everybody's good to hear? Okay, I'm going to multiply everything out then. And again, I'm going to do this kind of just in my head. I hope that's okay with you guys. And now let's combine our like terms and move everything onto one side. Yes.
You said x plus 3 squared, but I thought it was x minus 3 over x minus 2.
Oh, thank you. Good point. Copied that down wrong, huh? I'm glad you stopped me there. Okay. Okay, so 2x squared and x squared gives me 3x squared. I just have that 2x left. Negative 12 and negative 9 is negative 21, but I'm also going to subtract that 5 over to give me negative 26. Because I need it to be equal 0 to solve a quadratic, so I'm going to do that at the same time I'm combining all my like terms. Just so I don't have to write it out one more time. If you did it, if you do that in more than one step, surely that's fine, right? So now I could try to factor this, but since the leading coefficient is 1, I know it's going to be quite a bit of effort to try to factor this. Instead, what I'm just going to do is use the quadratic formula, because I know that's always going to work, and I'm not sure that, at least upon inspection, that this is factorable, and it's probably going to take just as much time to figure out if it's factorable as it would to just use the quadratic formula, so I'm just going to use the formula. In general, if the leading coefficient is 1, I typically just go to the quadratic formula because it seems like much less effort. Mackenzie, you still doing okay? Cool. Okay, so this gives me 18 over 6. I think the 316 I can do better than, 316 is 4 times 79. So I can make that a little bit better. The square root of 4 is 2. And so I can reduce this a little bit to make that a little bit nicer. But that's probably as good as I can do. And you notice I boxed this right away because when I had my factored form, all the denominators were monic things. So like clearly this kooky, crazy decimal with the square root in it isn't going to give me a 0 denominator anyway. So I just stopped at that point and boxed her up. It looked like I didn't check to see if it gave me a 0 denominator, but I did. I just did it real fast in my head because I remembered in the beginning everything was monic. Yeah, Mackenzie.
How do you find
It doesn't, you're plugging it back into all of them because any 0 denominator is enough to throw it out. So anytime any solution gives you any 0 in any denominator, it's bye-bye birdie for that one. But clearly this isn't going to give you a 0 anywhere, right? So, but yeah, that's a good question. Yeah, it doesn't matter which denominator, any denominator that gives you a 0. It's so long to that solution. Yeah.
Reduce the negative 1 to negative 2.
Well, reduced. The denominator turned into a 3 from a 6.
Yeah, I thought you used the 2 on the outside of the square root of 59.
So this is negative 2 over 6 plus or minus 2/9 over 6.
Okay.
So that becomes 1/3, and that becomes 1/3.
Okay. Okay.
Okay. So that's how I did that. Is that cool? All righty. Who's next? Happy to do more if you want to do some more. Emily.
Yeah.
I had to cheat.
It's number 6 of the chapter.
Sure. Yeah. No problem. One second, real quick here. It's getting kind of laggy. That'll help, I think. Okay. So this is an addition and subtraction problem. So the first thing I'd want to do is try to factor anything, specifically the denominator, so I can make a least common denominator. Doesn't take long for you to see there's no factoring that can really be done here. So let's find that least common denominator. I see 3 relatively prime factors, so my least common denominator is just going to be the product of those 3 denominators, since they're all relatively prime to one another. So far, so good? Okay. So if I look at the first fraction, I am missing the x and the 3x minus 1. Actually, I think this is going to get horizontally longer than it's going to get vertically. So I need to multiply that still by the x and the 3x minus 1. And then if I look at the next fraction, I'm missing the x minus 4 and the 3x minus 1. And I look at the third fraction, and I'm missing the x minus 4 and the x. And then all of that stuff is over my least common denominator. So far, so good, Em?
Yeah.
Okay. Question, can I reduce it this step? No. Why not? Because I have these addition signs that are outside of the parentheses. Fantastic. Very good. So what am I going to do instead? Multiply everything out, and then combine all my like terms, and then I can see if I can factor the new numerator and reduce that. So I'm going to just multiply these things out. I'm going to do it all in one step in my head, if that's okay with you guys, just to save us some writing. So let's see, we should 3x cubed. And then I have a 6x minus x, so that's 5x squared. And then minus, and then I have a x squared, so 6x squared. And then minus 12 minus 1 is minus 13. And then times 2 is minus 26. And then plus 4 times 2 is 8. And then we have plus 5x squared. All of that still over our common denominator. And let's see, combining like terms, I have 8x cubed. And then minus 20, so that's minus 9x squareds. And I have 2, so 28. So far, so good. So the last thing I'd want to do is try to factor that numerator to see if there's any reducing I can do. Since it has 4 terms, I check to see if I can factor it by grouping. Take a look at that. Is that factorable by grouping? No way, Jose, right? We should be able to do that just by inspection. So we're done. And since you did no reducing on this problem, there's no restrictions generated, so this is our final answer. Cool with that, Ems?
Yeah.
Just got kind of gnarly there, right?
Yeah.
A lot of symbols flying around, and depending on how good of you are with your mental multiplication with polynomials, could have taken a lot of steps there to kind of keep track of everything. So again, I don't guarantee I didn't make some stupid arithmetic error in there myself, but you know, you get the idea, right? So cool. Last call on questions, again, from any of the homeworks we've seen so far. Doesn't have to be just these last 2, but that would be my suspicion, is that most of the questions would be from the last 2. Okay. Oh, yeah, go ahead, Maddie.
Can you do number 10 on the third homework?
Sure. Which is just going to be x times x minus 3. So I multiply both sides of this by that least common denominator. And then I can reduce. So that's going to leave me with 2x plus x minus 3 equals x minus 1. And I'm going to combine like terms and multiply everything out. And then move everything onto one side. The quadratic that I'm left with, I can see is easily factorable, so I'm going to solve it by factoring. The 2 things that multiply to give me positive 3 and add to give me negative 4 are negative 3 and negative 1. So my solutions are 3 and 1. However, when I go back and try to check that, I notice that 3 and plug it in either of those 2 denominators, they give me a 0 denominator. So I'm going to discard that solution. That, and though with the 1, any denominator I plug that into, we're good. Okie dokies?
Yeah.
Cool. Oh.
Why doesn't x equals 3 a solution?
Because I get a 0 denominator with
okay.
when I plug 3 in for x into the original problem.
Oh, okay.
Right. The x minus 3s I highlighted with the 3 to show, trying to show why that was an issue. Cool. So we've seen a couple here now in the homework of these extraneous solutions, right? I think that you might have picked all the problems that have the extraneous solutions. I'm not sure any of the rest of them did. They don't happen very often. But I tried to make sure that I came up with some problems for the homework that does happen in, just so you get used to looking for it. All righty. On to the new stuff. So these last 2 topics that we're going to start are graphing topics. So the first topic we'll talk about is graphing simple rational functions. And I'm going to use the abbreviation SRF for simple rational function because, well, that's a lot of letters, and it's going to come up a number of times. And boy, it just makes my life easier if I can just write SRF rather than writing that all out. You know, it's a bit of a mouthful also. So let's start by defining what I mean by a simple rational function. I don't have to say that. So our simple rational function is a non-zero polynomial of degree 1 or less. Now, if it's degree 1, we don't need to say non-zero, but because it's or less, I'm going to say that because I don't want 0 as my numerator, because that's a stupid thing to try to graph because it's just a constant function over another degree 1 polynomial. So there's really two forms that we might write a simple rational function in. So we'll write our simple rational function in one of these two forms. Keep in mind these are still the same thing, right? If I made a common denominator in the first form and added a over x minus h plus k, I would turn into something like the second form. Or if I had the second form and I took the numerator and did polynomial division by the denominator, I would get something like the first form. So that's how we're moving back and forth between those two forms. Not really important that you know that, but I just wanted to reiterate that those are equivalent representations of the same thing. And the conversion back and forth is just making common denominator, doing polynomial division. Okay. The graph of a simple rational function has a couple of special key features that we need to be aware of. So the first one is called a vertical asymptote. I'm going to abbreviate that as VA. Again, that's going to come up a lot. That's a lot of letters and a bit of a mouthful. It's a heck of a lot easier just to say VA. You know what I mean? So a vertical asymptote is a type of infinite discontinuity. Do you guys remember talking about those in the first semester? We mentioned it very early in the very beginning of the semester, so if you forgot, that's okay. But it's essentially just a line the graph approaches, but does not, let's be more specific. Let's say a vertical line that the graph approaches, but does not cross. And remember, vertical is like up and down, right? Again, sometimes it's easy to forget that. And we'll draw some pictures here with some examples in it in a minute. So if you're not quite sure what you're picturing, it'll be clear in a moment. The second key feature is a horizontal asymptote. And just like the vertical asymptote, I'm going to abbreviate this one also. I'm going to call this HA. Now, a horizontal asymptote is not a type of discontinuity because it has to do with the y-coordinate rather than the x-coordinate. So we're just going to call this a horizontal line that the graph approaches but does not cross. Okay with that? And again, we'll see some pictures here in the examples to get you a feel for what exactly it is that we're talking about. But it's not a big deal. It's easy to deal with. So that's about all we need before we can do a procedure. Oops. Yeah, procedure. So the first thing we need to do is identify the vertical and horizontal asymptotes. So if we're in that first form, the vertical asymptote is just x equals h, and the horizontal asymptote is just y equals k. Pretty easy to deal with that. For the second form, the vertical asymptote is negative d over c, and the horizontal asymptote is a over c. If you look at these two equations for the vertical asymptote, where do you think these are coming from? Those are just the values that give us a zero denominator, right? Essentially, all you're doing is setting the denominator equal to 0 and solving, and that's going to give you your vertical asymptote. So if you prefer to think about things that way, that's okay. And the horizontal asymptote is essentially the quotient to a division problem, but that's a lot. It's not something that's trivial to do in your head or whatever, right? So the formulas are rather helpful there for the horizontal asymptote. So the next thing we'll do is we'll draw the horizontal and vertical asymptotes. And then we need to find 3 points on both sides of the vertical asymptote. And then we need to plot the points and draw our graph. And that's our procedure, which is pretty easy to do. I'll pause here for a minute as I see lots of pencils still going, so I'll give you guys a second or two to catch up here, and then we'll hit some examples up, and then start talking about the more general situation for this, where we are not quite as specific as what the polynomials have to look like. So let's start doing a couple of examples. So let's say we want to graph y equals 2 over x minus 3 plus 1. So the first thing we're going to do is identify the vertical and horizontal asymptotes. I notice from this problem that we're in that first form that we identified. So the vertical asymptote here is just going to be x equals h. And the h in this case is what value? Very close. It's positive 3. Remember that the formula is x minus h, so the h is going to be the opposite of whatever it appears in the problem. And then the horizontal asymptote was y equals k. The k value in this case is what? 1. And notice that in the formula that it's plus k, so the k is going to be whatever sign it appears in the problem. Everybody cool with that? This should remind you very much like finding the vertex for an absolute value function or a quadratic function, right? Where the h and k's followed the same kind of rule. Okay, let's make our xy table here. So I need 3 points, and then I'll have my vertical asymptote, and then I need 3 more points. Now the vertical asymptote, there's no point there, right? Because the graph cannot cross it. So there's no y-coordinate that'll pair with 3. So I'm just going to like shade that box in to remind myself that nothing goes there. So that's not going to get drawn anywhere on my graph. There's going to be no point that has an x-coordinate of 3. And now I just need to pick 3 numbers that are less than 3 and 3 numbers that are bigger than 3. No reason to be sneaky about this. I'm just going to pick really obvious, easy to deal with whole numbers. Right? You could pick crazy decimals or fractions if you wanted to, but like why? You know? Plus, I find that the closer you pick numbers to the vertical asymptote, the better picture you kind of get. So, how do I get the y coordinates after I pick the x coordinate? You just like plug them back in, right? So I just take my function, plug that value for x in, and then I can evaluate. So 0 minus 3 is negative 3. 2 over negative 3 is negative 2/3. Negative 2/3 plus 1 is positive 1/3. But since I'm graphing, I'm just going to write it as a decimal because it's much easier to graph stuff if they're decimals rather than fractions, right? And then I'm just going to kind of continue doing this. And I just went ahead and did that in my head. If you need to use your calculator to do those things, you're more than welcome to do that, right? It's faster for me to just do it in my head. than it is to pull up the calculator on the computer and like use my mouse and pick the numbers and jibba jabba, right? But you're welcome to use your calculator to come up with those points. That's not a big deal. Everybody's cool with that? What's the one thing you have to be careful about when putting this into your calculator? If you took this and you type in that, it is not going to give you the right answer. What's the issue? The 0 minus 3 needs to be in the denominator, so you need a parenthesis around that part. Right, so be careful there when you're typing it into your calculator. I expect most of you would have figured that out when you start getting kooky numbers, but it's worth reminding you. Okay, so we have everything we need. We can start drawing our graph, so I'm going to go ahead and do that. So let's see, I gotta go 1, 2, 3 up, 1 down, 1, 2, 3, 4, 5, 6 over. Now I need to put in my asymptote. So my vertical asymptote is at 3. So I'm going to find 3 on the x-axis and then just draw like straight up and straight down. 1 is my horizontal asymptote, so I'll find 1 on the y-axis and just kind of straight over. Everybody good with how we draw in those asymptotes? And usually we use a dashed line like this as the standard. And now I'm going to plot my points. So what do we got here? 0 and 0.3, 1 and 0, 2 and -1. So then I'm going to start by following my asymptote. I'll go through my points. Then I'll follow my other asymptote. So I would be picky about when you're drawing your graph to make sure that you have arrows at the ends, that you're not crossing the asymptotes, that you're kind of parallel to what the vertical or horizontal asymptote as you're drawing things, that it doesn't look like if I continued extending your arrow that it would be crossing anything. You see how mine are nice and parallel to the relative asymptote. So I will be a little bit picky about that if you're, if you draw something like this, I would be picky about that because it looks like if you just keep extending, you're going to cross, right? So just, it's not a big deal, but, you can be nice and accurate, that helps. Everybody okay with that idea? Now the other half to do, I still have 3 more points to plot. So I have 4, 3, 5, 2, and then 6 and 1/6. Okay, OneNote, anytime you want to start responding, that's cool. What did I do to make you so angry? I didn't really even do anything. All I did was click undo for a point. Oh, there we go. Boy, it took off a lot more than I wanted it to, huh? All right, well, whatever, jerkwad. It's fine. Again, I'm calling my computer the jerkwad, not any of you guys. So there we go. And all of the graphs are going to kind of look like this, where you have 2 arms to your graph. They're on opposite sides or opposite corners of the 2 asymptotes. Sometimes you'll have like upper left and bottom right, or you'll have bottom left and upper right, but you won't ever have like 2 on the top or 2 on the bottom. They'll always be like diagonal from each other like that. Everybody cool? Let's do one more example from the other form, and then we'll move on. Sound good? All right. I think this will be example B. So here we can see that our problem is in that other form. We'll start the exact same way. We'll look for the vertical asymptotes. So the vertical asymptote is going to be negative d over c. And the horizontal asymptote is going to be a over c. Everybody's cool there? Notice on this one, the formula, everything had plus signs, so everything is the same sign as what it appears. So that's not tricky or anything. So again, we'll draw our table with 3 points on either side of our vertical asymptote. And again, I'll shade in the value for the y-coordinate for the vertical asymptote to remind myself that's not a point that I'm plotting there. It's just kind of a placeholder. And then I'll just pick 3 values that are less than negative 2.5 and 3 values that are bigger. And now to find my y-coordinates, we'll just plug them back in. And here's a place where, again, if your mental math proves insufficient, that's not a big deal. I'm still going to try to do the mental math on it because I think it's kind of fun. But this is certainly a place where typing in your calculator is totally cool. Let's see, if I plug negative 5 in, I get negative 23 over negative 5. So that's going to be negative 4.6. And then I have negative 19 over negative 3. So that's going to be negative 6.3 repeating. And then I'm going to have negative 15 over negative 1. Oh, wait a minute. Maybe these are supposed to be positive. Let me check real quick. Yeah, these are all positives. Excuse me. That's better. All right, it's negative 11 over 1. So that's negative 11. That's going to be negative 7 over 3. So that is negative 2 1/3. And that's going to be negative 3 over 5. So that's just negative 0.6. Again, if you needed to use your calculator to do that, totally understandable, right? Make sure you get your parentheses right, though, on that. Or you use the fraction command. You could do that, too. Okay, then draw our graph here. Kind of big. I have to go all the way up to 15 and all the way down to 11. So I'm going to go by 2s on the y-axis. So 2, 4, 6, 8, 10, 12. And then 2, 4, 6, 8, 10, 12. And then 5, 6. Oh, I guess I don't need 6. So far, so good. My vertical is here at 2.5. Kind of put that stuff a little close together. Hindsight's 20/20, though. Oh, and my horizontal asymptote was at 2, I think, right? Got to put that in there. All right. So we have -3 and 15, -4 and 6.3, and then, oh my goodness gracious, guys, look what I did. So dumb. How much was the y-axis going up by? 4 instead of 2. Gosh darn it, I'm dumb. You ever make a mistake happen to me? All right. Next one, -2 and -11. -1 and -2.3. And then 0 and -0.6. And there's that one. Everybody cool? Relatively no big deal on this topic, right? Considerably easier than the things that we had been working on prior to this. One last thing to talk about with regard to simple rational functions. Last year going, oh my goodness, domain and range, that could be really hard. Not here. So the domain is just going to be everything except for the vertical asymptote. So depending on the notation you want to use, you could write this in either fashion. And the range also quite easy, everything except for the horizontal asymptote. And for us, this will be the preferred way that we're going to write it. That's the more formal notation for writing a domain and range. This being the honors class, that would be my expectation, that we're going to use that interval notation is what that's called, as opposed to the more informal kind of like set notation, or an informal version of what would be a set notation anyways. But they're equivalent, right? They mean the same thing. So if we go back to those previous two examples, we'd say the domain is everything except for -2.5. And the range is everything. Really easy, right? The hardest part for that was just making sure you have the domain, or the vertical and horizontal asymptote correct. If you can do that, you can do the domain and range. It's like no big deal. You feel okay doing that? Okay, splendid. We'll start here talking about the next topic here, which is general rational functions. And we have 15 minutes or something left, I think. I just want to get a little bit of a jump on this prior to the next class period. And again, just like simple rational functions, I'm going to abbreviate this as GRF for general rational function. And this is considerably more difficult than a simple rational function because you have a lot more crazy behaviors happening. And we're not even going to consider like all the possible situations here that could happen. We're going to be pretty careful here and really only deal with things that are plausibly easy enough to deal with in a class like this. So definition, a general rational function is a non-zero polynomial over a polynomial with degree greater than or equal to 1. So basically what this is saying, you can have any degree polynomial in the numerator and any degree polynomial in the denominator as long as it's at least 1. So now you can have like quadratics or cubics or quartics and stuff just rolling around all over the place in here, which makes life considerably hectic or more hectic, right? As we've seen the graphs of some of these bigger polynomials when we looked at solving last chapter, just graphing them on our calculator and looking at the behaviors, but they could do a lot of kooky stuff, right? And now you start dividing two of these things together and you can get some really bizarre behaviors. So let's talk about some key features. So the first one is a vertical asymptote. So to find your vertical asymptote, we want to set, we need to put one more adjective in there. We need to set the reduced version of the denominator equal to 0 and solve. We can also have something called a removable discontinuity. I abbreviate that as the RD. This is a single point missing from a curve. So you remember when we did domains and ranges first semester? Occasionally there'd just be like an open circle somewhere on the graph. That's basically what we're talking about when we talk about a removable discontinuity. So these removable discontinuities will be the same value as the restrictions that would be caused when we reduce a problem. We'll need the x-intercepts. To find those, we'll just set the reduced numerator equal to 0 and solve. And maybe the y-intercept. And that's not bad to find the y-intercept. You're just basically plugging 0 in for x and evaluating. And the last piece are the other asymptotes or end behaviors. So these other asymptotes, you can have a horizontal asymptote still, or you can have what's called like an oblique or slant asymptote. And that's basically like if you have a diagonal line that the graph approaches but does not cross. Now, an end behavior is a more general term for an asymptote. So end behaviors contain all your asymptotes, but they also contain other things. So remember how we have asymptotes cannot be crossed? So like, we have asymptote. This would be like an end behavior. Notice that for the green graph, it does cross the dashed red line, but eventually it starts following it as it goes out towards positive or negative infinity, right? So an end behavior is basically the same thing as an asymptote, but you might cross it once or twice in the middle, like near zero, like near the middle of the graph. But eventually, if x gets big enough or small enough, it's going to start following that end behavior. Is that okay with you guys? Now, I'm not going to be too picky about the notation we're using to differentiate between asymptote and end behavior. They're basically, we're going to treat them the same way. But I want to point out to you that there's a little bit of difference between the two. Okay? So there are three cases here that can happen. So if the degree of the numerator is greater than the degree of the denominator, we have the oblique asymptote. And we find this by using polynomial division. And we'll do some examples next time about specifically how we're getting that oblique asymptote out of the polynomial division. But I guess I should say asymptote or end behavior. It's possible you're getting some crossing going on there still. So if the degree of the numerator equals the degree of the denominator, here we have a horizontal asymptote or end behavior. And this is the leading coefficient of the numerator over the leading coefficient of the denominator. Is how we'll find that value for the asymptote or end behavior. And the last case is if the degree of the numerator is less than the degree of the denominator. Here again, we're going to have a horizontal asymptote or end behavior. It's usually not clear until you draw the graph which one you're going to have. And this one is easy because it's always going to be 0. Maybe I should just say y equals. We need to stop here because we're almost out of time, but this is a good start. So when we get next time, we'll take homework questions as usual, and then I'll go into some examples of graphing some of these things and helping to find these key points and piece together a decent XY table enough to get a good graph out of the thing. Okay? Cool beans, Daddy-O's.